The terraforming of Mars is a hypothetical procedure that would consist of a planetary engineering project, with the goal of transforming the planet from one hostile to terrestrial life to one that can sustainably host humans and other life forms free of protection or medication. The process would likely involve the rehabilitation of the planet's present climate, atmosphere and surface through a variety of resource-intensive initiatives and the installation of the novel ecological system. Explanations for choosing Mars over other potential terraforming targets include the presence of water and the geological history that suggests it once harbored a dense atmosphere similar to Earth's. Hazards and difficulties include low gravity, low light levels relative to Earth's, and the lack of a magnetic field. Primarily, the main reason for this outrageous mission is to decrease the odds of humanity's extinction by having concurrent settlement of other planets. Terraforming Mars would entail three major interlaced changes: building up the magnetosphere, building up the atmosphere, and raising the temperature. The atmosphere of Mars is relatively thin and has a very low surface pressure. Because its atmosphere consists mainly of carbon dioxide, once Mars begins to heat, the carbon dioxide may help to keep thermal energy near the surface. As it heats, more carbon dioxide should enter the atmosphere from the frozen reserves on the poles, enhancing the greenhouse effect. This means that the two processes of building the atmosphere and heating it would augment each other, favoring terraforming. However, it would be difficult to keep the atmosphere together because of the lack of a protective global magnetic field against erosion by the solar wind. Hey, I've made an outrageous goal to reach 5,000 subscribers by the end of 2020, and I need your help to get there. So if you're enjoying the content so far, be sure to subscribe. One method of augmenting the Martian atmosphere is to introduce ammonia. Large amounts of ammonia are likely to exist in frozen form on minor planets orbiting in the outer solar system. It might be possible to redirect the orbits of these minor planets or smaller ammonia-rich objects so they collide with Mars, thereby transferring the ammonia into the Martian atmosphere. However, ammonia is not stable in the Martian atmosphere. It breaks down into diatomic nitrogen and hydrogen after a few hours. Thus, though ammonia is a powerful greenhouse gas, it is unlikely to generate much planetary warming. Presumably, the nitrogen gas would eventually be depleted by the same processes that stripped up Mars of much of its original atmosphere. But these processes are thought to have required hundreds of millions of years. Being much lighter, the hydrogen would be removed much more quickly. Carbon dioxide is 2.5 times the density of ammonia, and nitrogen gas, which Mars barely holds onto, is more than 1.5 times the density, so any imported ammonia that did not break down would also be lost quickly into space. Another way to create a Martian atmosphere would be to import methane or other hydrocarbons, which are common in Titan's atmosphere and on its surface. The methane could be vented into the atmosphere, where it would act to compound the greenhouse effect. However, like ammonia, methane is a relatively light gas. It is in fact even less dense than ammonia, and so would similarly be lost into space if it was introduced, and at a faster rate than ammonia. Even if a method could be found to prevent it escaping into space, methane can exist in the Martian atmosphere for only a limited period before it is destroyed. Estimates of its lifetime range from 7 months to 4 years. Especially powerful greenhouse gases such as sulfur hexafluoride, chlorofluorocarbons, or perfluorocarbons have been suggested both as means of initially warming Mars and of maintaining long-term climate stability. These gases are proposed for introduction because they generate a greenhouse effect 1,000 times stronger than that of carbon dioxide. Fluorine-based compounds such as sulfur hexafluoride are desirable to chlorine-based ones, as the latter destroys ozone. It has been estimated that approximately 0.3 microbars of CFCs would need to be introduced into Mars' atmosphere in order to sublimate the South Polar CO2 glaciers. This is equivalent to a mass of approximately 39 million tons. That is about 3 times the amount of CFCs manufactured on Earth from 1972 to 1992. Maintaining the temperature would require continual production of such compounds as they are destroyed due to photolysis. It has been estimated that introducing 170 kilotons of optimal greenhouse compounds annually would be sufficient to maintain a 70k greenhouse effect given a terraformed atmosphere with Earth-like pressure and composition. Typical proposals envision producing the gases on Mars using locally extracted materials, nuclear power, and a significant industrial effort. The potential for mining fluorine-containing minerals to obtain the raw material necessary for the production of CFCs and PFCs is supported by mineralogical surveys of Mars that estimate the elemental presence of fluorine in the bulk composition of Mars at 32 parts per million by mass, as compared to 19.4 parts per million for the Earth. Alternatively, CFCs might be introduced by sending rockets with payloads of compressed CFCs on collision courses with Mars. When the rockets crashed into the surface, they would release their payloads into the atmosphere. A steady barrage of these CFC rockets would need to be sustained for a little over a decade while Mars changed chemically and became warmer. Mirrors made of thin aluminized PET film could be placed in the orbit around Mars to increase the total insulation it receives. This would direct the sunlight onto the surface and could increase Mars surface temperature directly. The 125 km radius mirror could be positioned as a steatite, using its effectiveness as a solar cell to orbit in a stationary position relative to Mars near the poles to sublimate the carbon dioxide ice sheet and contribute to the warming greenhouse effect. Reducing the reflective power, also known as albedo, of the Martian surface would also make more efficient use of incoming sunlight in terms of heat absorption. This could be done by spreading dark dust from Mars moons, which are among the blackest bodies in the solar system, or by introducing dark extremophile microbial life forms such as lichens, algae, and bacteria. The ground would then absorb more sunlight, warming the atmosphere. However, Mars is already the second darkest planet in the solar system, absorbing over 70% of incoming sunlight, so the scope for darkening it further is very small. If algae or other green life were established, it would also contribute a small amount of oxygen to the atmosphere, though not enough to allow humans to breathe. The conversion process to produce oxygen is highly reliant upon water, without which the carbon dioxide is mostly converted to carbohydrates. In addition, because on Mars atmospheric oxygen is lost into space, unlike Earth where there is an oxygen cycle, this would represent a permanent loss from the planet. For both of these reasons, it would be necessary to cultivate such life inside a closed system. This would decrease the albedo of the closed system, assuming the growth had a lower albedo than the Martian soil, but would not affect the albedo of the planet as a whole. On April 26, 2012, scientists reported that lichens survived and showed remarkable results on the adaptation capacity of photosynthetic activity within the stimulation time of 34 days under Martian conditions in the Mars Stimulation Laboratory maintained by the German Aerospace Center. One final issue with the albedo reduction is the common Martian dust storms. These cover the entire planet for weeks and not only increase the albedo but block sunlight from reaching the surface. This has been observed to cause a surface temperature drop which the planet takes months to recover from. Once the dust settles, it then covers whatever it lands on, effectively erasing the albedo reduction material from the view of the sun. Since 2014, the NASA Institute for Advanced Concepts Program and Techshot Inc. are working together to develop sealed biodomes that would employ colonies of oxygen-producing cyanobacteria and algae for the production of molecular oxygen on the Martian soil. But first, they will need to test if it works on a small scale on Mars. The proposal is called a Mars Ecopoiesis testbed. Eugene Bolland is the chief scientist at Techshot. He and his team intend to send small canisters of extremophile photosynthetic algae and cyanobacteria aboard a future rover mission. The rover would corkscrew a 7 cm canisters into selected sites likely to experience transients of liquid water, drawing some Martian soil, and then release oxygen-producing microorganisms to grow within the sealed soil. The hardware would use Martian subsurface ice as it changes into liquid water. The system would then look for oxygen given off as metabolic byproduct and report results to a Mars orbiting relay satellite. If this experiment works on Mars, they will propose to build several large and sealed structures called biodomes to produce and harvest oxygen for a future human mission to Mars life support systems. Being able to create oxygen there would provide a huge drop in cost to NASA and allow for longer human visits to Mars compared to the current situation where astronauts have to transport their own heavy oxygen tanks. This biological process called Ecopoiesis would be isolated in contained areas and is now meant as a type of global planetary engineering for terraforming of Mars' atmosphere. But NASA states that this will be the first major leap from laboratory studies into the implementation of experimental as opposed to analytical planetary in situ research of the greatest interest to planetary biology, ecopoiesis and terraforming. One key aspect of terraforming Mars is to protect the atmosphere from being lost into space. Some scientists hypothesize that creating a planet-wide artificial magnetosphere would be helpful in resolving this issue. According to two Japanese scientists, it is feasible to do that with current technology by building a system of refrigerated latitudinal superconducting rings, each carrying a sufficient amount of direct current. In the same report, it is claimed that the economic impact of the system can be minimized by using it also as a planetary energy transfer and storage system. During the Planetary Science Vision 2050 workshop in late February 2017, NASA scientist Jim Green proposed the concept of placing a magnetic dipole field between the planet and the Sun to protect it from high-energy solar particles. It would create a partial and distance artificial magnetosphere. The field would need to be Earth comparable and sustain 50 microtesla as measured at 1 Earth radius. The paper abstract cites that this could be achieved by a magnet with a strength of 1 to 2 teslas. If constructed, the shield may allow the planet to restore its atmosphere. Simulations indicate that within years, the planet would be able to achieve half the atmospheric pressure of Earth. Without solar winds stripping away at the planet, frozen carbon dioxide at the ice caps on either pole would begin to change from solid into a gas and warm the equator. Ice caps would begin to melt to form an ocean. The researcher further argues that volcanic outgassing, which to some degree balances the current atmospheric loss to Earth, would replenish the atmosphere over time, enough to melt the ice caps and fill 1/7 of Mars' prehistoric oceans. Don't forget to subscribe to help me reach my goal of 5,000 subscribers. It's free and you can always unsubscribe. See you in the next video.